Hey, this is Dr. B, and in this lecture we'll talk about some important background material in order to understand nuclear medicine. We'll be talking about nuclear processes, and this should help you understand how nuclear medicine is an important tool both for imaging and for therapy. Any nuclear process begins with a radionuclide, that is an unstable nucleus, sometimes called radioactive. It's a substance which will eject something from its nucleus. Notice nuclear processes do that, but chemical processes do not. In a chemical process, the nucleus is maintained. And if we're going to look at it, let's do a quick review of atoms in general. Most people know the three common subatomic particles of an atom. Protons with a positive charge, meaning they are attracted to electrons, so we give them a negative charge, and are neither attracted nor repulsed by neutrons. Protons and neutrons are in the nucleus, the electrons are outside. The proton and neutron are approximately the same size and mass. The electron is up to 1,000 times smaller. The electron cannot be further subdivided as far as we know. We call that an elementary matter particle. And here's a look at the standard model of elementary particles, which is way more detailed than we really want to go into. But hey, there it is, right? So if you really want to know a lot about an atom, there you go. You can't get much more detailed than this. The protons and the neutrons are not believed to be elementary particles. They have inside them, if you will, and that's probably a lousy way of describing it, up quarks, down quarks, and gluons, and I won't bother saying what those are, except that they are considered to be these two fermions, which means they're matter particles, but the gluons are really just energy. They're considered to be force particles. And if you want to go further, this model, in case you're curious, has 12 different types of matter particles and 5 different types of force particles, including the infamous Higgs boson. So I'll just stop there. This is a nuclear study, not a physics study. But if you got an unstable nuclei, we call that a radionuclide. They're great for imaging as well as for therapy. They have a couple things in common. They oftentimes, but not always, have too many neutrons in the nucleus, meaning more than 1.5 times as many. Don't take this as a hard fact, but it's something that's generally observed, certainly not always. But it is true that all isotopes of all elements above 83 are unstable. They're radionuclides. It's also true that technetium, for reasons that aren't well understood, every one of those isotopes, even though it's atomic number 42, or is it 43? Well, regardless, all of those isotopes are unstable. So you've got yourself a radionuclide. It's going to fall apart. What's it going to eject? Well, a variety of things. It might eject an alpha particle. This is a helium nuclei. That means no electrons. 2 plus means it's lost its 2 electrons. It is helium because it is atomic number 2, 2 protons. That's the atomic number, just the number of protons. And it also has 2 neutrons. I know that because the mass number, meaning protons plus neutrons, is 4. So to get the number of neutrons, just do top minus bottom. Mass number minus atomic number. It's a shame that it's hiding within. In any event, it might kick out an alpha particle, fine. It might kick out a beta particle. And this is not an electron. This is an electron, but also a case where a proton has been converted to a neutron. I know that because it's -1 in terms of protons. That's just nomenclature to show you that it's lost a proton. That's called a beta particle. Pretty weird. This is not as weird because it has no mass, no protons, no neutrons. It's just a form of energy known as a gamma ray or wave. I don't feel comfortable calling it a gamma particle, but I guess energy exists in particles as well. This is similar to a beta particle, only with a +1 rather than -1. We call that a positron, meaning that in addition to ejecting an electron, it also has a neutron converted to a proton. Finally, we have garden variety neutrons, right? No protons, 1 neutron. We can also have proton emission, just a proton, no neutrons. Those are the nuclear decay particles. Let's have a look at them here. So you've got some sort of atom. It can kick out a proton. We call that proton emission, which is relatively rare. It can kick out a neutron, which we see here, and this is more often a case where you have some fission going on. Those substances that do that could be neutron sources. Those accelerate nuclear processes. If you had a substance that absorbs a neutron, and they exist, those can slow down a neutron, a nuclear process. Very important if you're working, say, in Waterford, Connecticut, 20 miles from my house, to avoid a meltdown. It can kick out an electron and subsequently have a neutron converted to a proton. We call that beta emission. If instead the proton is converted to a neutron, we call that beta plus emission. And I may have gotten the proton to neutron transfer incorrect here. This is correct here. So make sure that you know that you're dealing with the difference between positron emission and beta emission. Let's continue. We might also have an alpha particle emitted. We've shown what that is right there. And finally, you could just have gamma emission, which is just emission of some energy. All of these show up in either imaging or therapy techniques. This is a background to nuclear medicine.